Hey everybody, Shawn here from the Automation Blog and School, and in this episode of the Automation Podcast, I meet up with Ivan Mohler from PiControl to learn all about their stepless, multivariable, closed-loop PID tuning software, which you'll hear him refer to as a closed-loop system identification software package. Ivan, thank you for coming on the Automation Podcast to talk to us about PiControl and your solutions for automation. But before we get into that, could you first start, before jumping into your presentation, telling us a little bit about your role at PiControl Solutions?
Okay, thank you. Greetings to everyone and nice to join you. Actually, I am a senior process control engineer at PiControl Solutions, and I'm working for PiControl for last, I would say, 10 years. Have a PhD in process control, graduated chemical engineering, similar field, and yeah, I'm excited to be a part of this podcast and let's see what we can do.
Excellent. Yeah, so you definitely have the experience with the company, but also the degree and the deep understanding of what we're going to talk about. So I look forward to seeing what we're going to discuss today.
Okay, so actually today I would like to present you a stepless multivariable closed-loop system identification software and technology in one side, and on another side it is also a PID tuning and APC design and optimization technology as well.
Excellent.
Okay, so before we start and jump immediately to the technology, please give me a couple of minutes just to give a brief explanation of a PiControl solution company, who we are and actually what we are doing. So actually we are a process control technology producers. We are OEM of process control software technology, which mostly tackles with the process control performance monitoring, process control performance diagnostics, process control tuning and optimization. And actually we are going into the layers which are considered like a primary process control layers, where you can have a typical PIDs like lever temperatures, analyzer controllers, and so on. Also, we tackled with advanced process control, which is designed in the DCS or a PLC. And also we are maintaining and improving the existing or actually new model predictive controllers from a typical famous companies like AspenTech or Honeywell or some others. Also, we are, I would say, 30 plus years experts in primary and advanced process control. And we have embedded, commissioned, and started more than 100 DCS-based APC projects, or maybe model predictive controller projects, PID tuning projects, system identification projects, and so on. And we have been maybe more than 100 different manufacturing and chemical plants all over the world. And we are proudly to say that we are worldwide leaders in industrial remote process control training, where actually we teach primary control, advanced process control, model predictive control, design and optimization, system identification techniques, and some other training courses as well. We have been formed 1997, headquarters in Texas, Houston, and actually we have several regional offices all around the world. Maybe the most famous and important offices are in Europe, Belgium, and Croatia. Asian office, it is situated in India, Mumbai, and in South America, we are actually in Mexico. So mostly with that, actually, I would like just to give a brief list of the technology, what actually we can offer and we offer. And actually we have invented a new technology for multivariable complete closed loop system identification, covering our two software products, PyTops and Columba. Then we have a multi-objective PID tuning and advanced process control design and optimization technology, which is inside of the PyTops. We have online process control in all layers, PIDs, advanced process controller, and model predictive controller performance monitoring and diagnostic technology, which is called Apromon. And we have created completely different auto-tuning package called SuperTune. It is actually automatic adaptive auto-tuning package, which actually does not require step changes or set point changes of the PID controllers at all. And also, we are huge in simulation packages. We are closely cooperating with the many universities worldwide, and we are creating real-time process control training and simulation packages like a product called SimSet, then PiDistill and Batch Distill products, and so on. And just to give you a brief introduction and variety of our company customers like ExxonMobil, then Intel, Sunoco. There is a famous European refinery group called MOL. Then our partners are LG Chemicals. We have developed some technology for National Oilwell Varco and for some kind of industrial electric power plants like AES Andres and Florida power plants. We have done many APC projects and tuning projects for Southampton Resources. Also, we are big in pharmaceuticals, tuning batch reactors and dryers and distillation columns. We have done advanced process control for APF. This is Indonesian polymer company, and also for the Westrock. Also, some clients like DCS or PLC companies likes to use our technology during their maintenance of the projects or startup, like ABB Honeywell. We are closely cooperating with Atlas Copco, I would say very big compressor company, especially in the USA. A huge chemical company in India, Aditya Birla. Then some other like paper companies, polyethylene companies, and natural gases from Canada. These are natural resources, so-called. So yeah, actually this is like a brief introduction to the company. I don't want to waste too many slides on the introduction. Let us maybe skip immediately to the technology, what we actually agreed to present today. Okay?
Sounds good.
Okay, so actually today I would like to present a stepless multivariable closed loop system identification technology which does all the calculation in time domain. So there is no Laplace domain, frequency domain, and complicated parameters like alpha, beta, zeta, gamma, and so on. So everything what you will see today, it is completely in milliseconds, seconds, minutes, and hours, like it should be in any kind of the process control room. So actually, to give you a brief introduction about the technology, so as you are aware of many technology in the area of system identification, PID tuning, or maybe advanced process control design, before they start to design anything or before they try to calculate any kind of the models, they need to do a lot of step testing in the plant. And there are a lot of software competitors which need to put PID controller in manual mode, and then in the way of the steps, they will actually try to bump the valve position maybe from 3 to 5%, 5 to 10%, 10 to 15%, wait for the response of the control variable like temperatures, levels, flows, and so on. And then they will gather the data. And actually this kind of the step testing for them, it will take approximately 2 to 3 weeks, and they will come into the plant and they will try to just do step testing for 2 weeks. Some other competitors brag about the technology where they can actually do closed loop system identification technology, but actually what they can do, they can only put controller in automatic mode and do the similar step changes on the set points. And
I'm going to
many
interrupt.
times,
I'm going to interrupt for a
yeah,
second
please.
because I know our audio-only audience can't see the charts, which are very informative. And just talk about the software. For instance, an old package I used, RSTune. You really needed to get all the parameters. You had to. I remember doing this late at night on a water treatment facility. Is you had to bump the output. You had to say, okay, well, we're currently, outputting this many gallons per second. We need to bump that and watch how the process variable changes to know what our lag time is, to know all these variables, and enable and for us to tune the loop, we had to do that. And this was the lag time in this process, lots of long pipes. It took a long time. It took, it didn't take a week, but it took most of the night to actually go through this process. So having to bump or step up the variables to be able to do the tuning, that can be very time consuming. So I just wanted to kind of back up what you were saying, Ivan, and with that kind of personal experience to talk about that.
Yeah, actually, you're right. And many times when we are seeing model predictive controller projects or advanced process controller projects in the different manner designed, actually you want to stabilize and improve the moneymaker controllers, which are definitely slow controllers, sluggish controllers, like analyzer controllers, temperature controllers, maybe slow but important pressure controllers. And doing many step changes on this kind of the controllers, it is really time consuming job. And many times you will need to go outside of the boundaries of
Hmm.
some kind of the safety boundaries, and you will need to do maybe larger step changes. Then you will upset the plant. Maybe the plant will need to go to some lower capacity
Hmm.
operation, and many times this is not desirable, because typically in the nowadays plants, one heater is a heater for one unit, but it is a cooler for another unit.
Mm.
So plants are heavily intercycled, and everything is like a recycle. So if you bump something on one side, it can cause five different things to oscillate.
Yeah.
So definitely this is not a way. If you can avoid step tests, definitely it is a process which needs to be avoided. And actually I would like to talk about today how to reduce the number of step tests, actually how to use data which are saved in the data historians. And actually I would like to say that this data is really gold mined for the system identification tools and for the system identification personnel. Not only that, there are plants where actually you cannot do step changes. So consider like a polyethylene reactor, very exothermic reaction. If you put controller in manual, you will get a runaway process. Automatically, you will need to shut down the reactor. Or maybe in some cases, uh, take a look at the boilers or the controls of the boilers.
Hmm.
So there needs to be very tight control of the levels and pressures and everything, and you need to control the turbine speed at the specific RPMs and so on. So the room for the step tests in these plants actually is not there. There are plants which are actually pushed to the maximum of the capacity or very close to the maximum of the capacity. So there is no room for extra step tests, because all the controllers are fighting against their natural limits. Is it the valve position? Is it maybe non-linearity region in the distillation column or something else? So there are many reasons why actually it's just a typical step testing when you are trying to put controller in manual and bump a valve, not only for one time, you need to do it for several times, up
Hmm.
and down, different scenarios, 3%, 5%, and so on. So definitely you can consider a lot of case examples when this is not so appreciated, and people do not like it, because for 2 weeks, if you are doing step tests and if you are actually doing intrusive step tests, then you're actually making a lot of spec off or undesirable material or
Hmm.
conditions inside of that plant. And this is all the waste of the money, right?
Yeah.
So that's why definitely I would like to talk about some other slightly different approach what PiControl has created and what we are promoting to the world. And actually, we have a system identification technology which we consider like a full-blown system identification technology. One thing what I need to demystify is many vendors like to say they can do closed-loop system identification, but closed-loop system identification is not just put controller in automatic mode and do a set point change. Closed loop system identification is also to take completely oscillatory controller in automatic mode. Closed loop system identification is also to gather the data where the controller is placed in the cascade mode, not to break a chain, not to put controller in automatic or manual mode, and not to do additional step tests. Closed loop system identification is also when you have a MPC controller which is on and running, just to take this data and to improve the existing MPC models, not to create or turn off the MPC controller and then again for 1 or 2 weeks do step changes. So all these things are considered as a closed loop system identification, And we are proudly to say that we can do all these things what I have just mentioned.
I want to ask you a question. You keep saying system identification. Can you paraphrase that, because I think that conjures up something something different than what you're talking about. So could you paraphrase what you mean by system identification?
Okay, so in the process control arena, system identification is actually the procedure or the method of finding the optimal parameters for the process model which you want to identify.
Excellent.
So let's say if we have a flow controller, a typical simple case example, or we can use a temperature controller. So in order to find the process model, which will describe the behavior between the valve and the temperature probe or temperature measurement, we need to have a process model, or I would say a model which will give a nice dynamical and static explanation between these two variables. And we are doing that using different system identification technologies. Some of them call this like a model identification. Some of them call this like a process identification. But since system can be everything, I'm just using a general abbreviation like a system identification.
Yeah, you're modeling the process. You're modeling what happens when things when as changes occur, and I think you explained it extremely well. Thank you.
Okay, so actually what I'm trying to say with the third picture that we can do and we can identify process models many times without doing any kind of the step tests in the plant, many times without breaking the cascade chain, many times without turning off the MPC controllers and just taking the ugly behavior of a control or control loop data and turning this in a nice and accurate process model.
So what we're seeing
And
here on the screen for the audio audience is we're seeing what you would typically see if you plotted the process variable and control variable, where the process variable is kind of doing its thing and the control variable is all over the place because it's trying to get the process variable to go in a direction it wants to go. So it's going higher or going lower, and so that would be your standard what you would see in many untuned loops. You would see this would be very crazy because the control variable is really trying to go in many different directions to try to bring the process variable to the set points.
yes, exactly. So let me actually try to give you a list of the things what normally we do and we can do. So our new system identification technology mostly uses past data which are saved in any kind of the PLC or DCS historians. Today we know that many plants have historians that are collecting, saving the data, doing different analyses, making trends and charts from this data. And actually the behavior from the uh, past plant performance saved in the way of the data, it is an excellent actually choice of getting the models, because with that you can get whatever you want. You can just scroll down to 6 months in the past, and you will see some kind of the cause and effect. Because in the real system identification, if you want to identify the model, you always need to have some cause and effect relationship. If this is not there, then there is no tool in the world which can do any kind of the modeling part. So what we are doing, we are going inside of the data historian, whatever it is, DCS or PLC, looking at the normal plant operation data, looking at the startup, shutdown part of the operation, and actually taking the useful data where there is some visible cause and effect in the data. And from this data, actually, we can identify accurate process models using even open loop or completely closed loop data, where loops are being completely set in automatic or kept in cascade mode without the need of breaking cascade chain. We can have a completely oscillatory controller behavior impacted with the high noise and unmeasured disturbances. And with this kind of the data, we are able actually to identify the true process model and isolate unmeasured disturbances from the true process model. Then also we can identify the true process model from the loops which have a significant or even small valve issues like extinction, deadband, hysteresis. But not only that, simultaneously, what we can do, we can also identify the amount of the valve problems. Okay?
Now, let me ask you this. I think everybody understands oscillatory or valve issues, noise issues. Can you? But I don't know that everybody's familiar with the cascade mode, which a lot of people have standalone loops, right? So they never get into that. Could you just spend a second on what you mean by cascade mode?
Okay, not a problem. So I would say if you consider any kind of the manufacturing plant or chemical plant, 1/5 of the controllers are actually cascade controllers. And by that, what I mean, let's say you have a temperature controller of distillation column, and you have also reflux as a flow which is coming back to the distillation column, like a recycle to increase the efficiency of the distillation column. So normally in this kind of the distillation columns, you are measuring the temperature because the temperature is a pure sign of your purity or a property, what you want to distillate. And actually, many times you also want to control the flow of the reflux, which is coming back to the distillation column. And the control strategy many times applied, it is actually you are cascading the logic from the temperature controller to the flow controller. So in that way, you have two controllers serially connected. And actually you have a master controller, which is considered like a main temperature controller when you want to have a tight set point. And you have like a slave or secondary controller, which is considered to be a flow controller, which is helping you to achieve better cooling, where the set point or the order, how much flow of the reflux you want to add to the distillation column will come from the main temperature controller. So this is actually considered as a cascade controllers. In the PLC world, many times cascade mode, it is called like auto remote mode. And auto local mode is called like a complete automatic mode. Okay?
Okay, that's good.
And in the DCS world, many times instead of the auto remote mode, you have an option which is called the cascade mode. But both things are the same.
Okay.
Okay?
Excellent.
So also what we can do and what we have done many times, we are not MPC hardware or software producers, but actually we are producers of the technology which can improve existing model predictive controller models when these controllers are completely running and on. And with that, we can just gather past data, again, without doing any kind of the additional and time-consuming and intrusive step tests in the plant. We can do completely simultaneous multivariable system identification. By multivariable system identification, I obviously mean, let's say example, maybe there is a distillation feed, there is reboiler steam flow, and there is a reflux flow, and all these three flows can simultaneously impact on the distillation temperature. So you're gathering more than one variable, placing them inside of the system identification tool or a method, and trying to simultaneously identify more than one model, and actually trying to present over these several models the significance or the impact from each flow to the temperature. Okay?
Yes.
Okay, excellent. And also what we can do, we can, using our system identification tool, we can actually process nonlinear processes where actually the principle of linear superposition is slightly broken. So normally for any kind of the control strategy, like a PID strategy or APC strategy, many times or also in the MPC world, you want, and it is good to have a linear behavior of the variables. But definitely we know that manufacturing plants and chemical plants are not so linear, and they have non-linear regions, and we can help to identify the models and in which regions of the plant operation these models will work, and at which regions you need to identify different models, considering this as a non-linear approach or a non-linear process. Also, one thing what we can do, and this is a powerful thing, in each plant there are a lot of experienced operators, chemical engineers, people, technicians, and other remaining people in the plant who actually know the process. They know the process sensitivity, they know the process dynamics and everything. And what we are able to do, we are able to quickly talk with them, just state the right questions, and with this powerful information what we are getting from them, we are able to incorporate this information, which is like a process information and dynamics information, inside of the system identification tool, to help the system identification tool to go into the region where actually this information is valuable. So in a simplified manner, actually, we are talking with operators and process engineers, and we are taking their answers, plunging these answers into system identification tool and identify accurate process model without looking at the past data or without doing additional step tests. And for a small chat or for a small conversation, you need 5 to 10 minutes in order to extract good information from a good process engineer or operator. But to do the same step tests in the plant, you will need 2 weeks. So this is another very useful approach what we can do, because we can play with all model parameters what we like to identify, and actually with that we can shuffle and tackle with many different case scenarios. Also, we can conduct what-if analysis to compare model predictions with the real process variables, even with the realistic or non-realistic situations. And with all these things said, actually what we are trying to do, we are trying to keep plant in the desired operation mode. We are trying to prevent intrusive and time-consuming step tests in the plant, which will actually give you a lot of spec off or undesirable conditions. And we are also trying to speed up or reduce the amount of time consumed at any kind of the project. Okay?
Yeah, that's a good summary.
Okay. So with that, actually, I have 5 different examples taken like a print screens or screenshots from our technology, where actually in each example, I will try to give some kind of the explanation and summary and the benefits from these kind of the examples. So the first example where we are doing completely closed loop system identification was using the data from one polymer reactor. So as you can see, there are 2 trends on this picture. Above trend, the red line presents pressure measurement inside of the polymer reactor, and the bottom trend presents the steam valve position. Okay. So as you can see from both of the trends, this is completely unstable controller behavior, where controller was and still it is in automatic mode of operation. But as you can see, pressure continuously cycles around some value, and it is impossible to make improvements of this pressure controller. If you take a look at the valve position, at the first part of the trend, you will see that there are a lot of spikes in the valve position. Then the remaining part of the data, you will see cycling in the valve position. And also you will see that the valve operation, it is around maybe 0 to 10%, because you see that many times the valve position hits 0. So you have a lot of constraints or limitations in the process, and you have completely unstable conditions in the process. And this controller is completely in automatic mode. And you do not see a set point change here. We haven't done any set point change here. We haven't done any kind of the step test here. We were just looking at the data historian. We saw this part of the data, we taken this part of the data, plunged the data from the Excel inside of our tool. And as you can see, we could create a, I would say, quite impressive and very accurate process model, which matches with the red line, which is just a pressure measurement, right?
Yeah, and for the audio audience, I mean, this is your typical oscillating loop where your control variable is just oscillating all over the place to try to get the process variable to hit a set point, and it never does. It just keeps oscillating.
Yeah. So this is one example actually where we haven't we actually haven't put this controller in manual mode or create a set point change or didn't move a valve position for several times and maybe cause some problems in the plant. We have just taken a look at the data from the data historian, saw a good portion of the data, imported, this data has been imported to Excel, it was plunged in our technology, and then the remaining part was just to identify the mode. So this is first example. Then the second example, it is a closed loop system identification. It is a refinery distillation column. So refinery example, where actually you will see, and you can see three trends. So what we are doing, we are taking a flow controller. Okay, it is maybe a simple controller, but we are keeping this flow controller in automatic remote control mode or a cascade mode, where actually on the third trend, you can see very ugly set point trajectory, which is not like a step test or it is not a flat line, but is completely oscillatory set point behavior with, I would say, several huge spikes. So this is where the flow controller is kept in cascade mode and the operation went how it went. And the first trend, it is again completely oscillatory and unstable behavior of a flow. And the middle trend, it is the similar valve position. So what we have done, and I would say that 25% of all industrial PID controllers are actually cascade controllers, slave or secondary controllers, and they will have, or you will observe a similar behavior in this kind of the controllers. So what we have done, again, we took a look at the data historian, took a portion of this data without breaking a cascade chain, putting this controller in an automatic mode or even in manual mode without any need for any kind of the step test. We plunged the data in the technology, and as you can see, we got, I would say, a perfect match. Very excellent model behavior presented in blue, which is matching and following the trajectory of a process or a flow measurement, right? So this is extra ability which I feel that no other technology can do, to keep controllers in the desired mode, not to do set point changes or any kind of the step changes, just take past data and get accurate process model from the ugly behavior of the controller or ugly performance of the controller. And in this example, definitely you can convince the audience that definitely it's not a very nice response, right?
Yeah.
So this is the second example. Then the third example, it is again a system identification from the paper plant, where actually we have two trends. The bottom trend, in the bottom trend, you are actually seeing some kind of the step changes. And yes, in this example, there were step changes in the plant from the steam pressure controller set point. But the master controller was actually a boiling point rise controller, which is a property which needs to be tightly controlled in the paper plants. So as you can see, the first trend or the measurement behavior of the data, you would see data heavily impacted with the noise, spikes, drifts, some unmeasured phase disturbances, maybe even outliers produced from the electrical side of the hardware or the software or something else. So very ugly data. And many times if you try to compare the set point changes from your manipulated variables at the bottom and the responses of this control variable, what we are trying to identify, you cannot find a good match, good correlation, and you feel that actually this data first needs to be heavily preconditioned, filtered, or maybe something else, and then maybe you will get out something of this data, but it's not so promising, right?
Yeah,
So
and just for the audio audience, I mean the bottom the set point is very stepped, right? It just takes very normal steps. Um, the control variable looks like a seismograph. I mean, that's how crazy it is up and down.
yeah.
But go ahead, Ivan.
Yeah, so actually, the technology what we use for system identification is not sensitive to the amount of noise in the data, unmeasured spikes, disturbances, drifts in the data. So automatically you can run it and use it, and it will automatically isolate and not take into account all these data issues, what normally you can see in any kind of the plant, but it will isolate pure process model, which you can see on the blue trend in the middle, where actually you can see an excellent match, or I would say very good and satisfactory match between the measurement and the model what we are trying to identify. So this is again another benefit what you can get even if you have a ugly data like this. Then another case, it is a system identification from the power plant. And here what we are doing, we are simultaneously identifying process model and also disturbance model, again, based on completely closed loop system identification technique using completely closed loop data. So at the first trend, the red line, what you can see a turbine speed. And normally, if you understand and know the power plants and their regulations, they need tightly to control the turbine speed around 3,600 RPM. And it cannot fluctuate, it cannot up or down. And actually, there is some kind of the rule inside of the, or a regulation inside of the power plants. If your turbine speed goes below something like maybe 3598 or 3589 RPM, automatically you will need to trip and shut down the turbine. And this is probably not a good idea to do. But actually, this turbine speed was, and it still is, controlled with the steam valve position, what you can see in the second trend. And this is a pure closed loop behavior, feedback action of the controller. There is no set point change because you cannot have a set point change if you want to tightly control RPMs at 3,600. And the bottom trend, the third trend, it is actually a measured disturbance. But what this disturbance is, it is a megawatt power load. So it is disturbance which is coming from the grid, either from the other portion of the plant or maybe some other plant, or either from the city. And you cannot step this disturbance. Actually, there is no disturbance which you can step because disturbances are probably variables which cannot be controlled or stepped, but they will behave like they will behave, right? Mm-hmm. In some cases, they will be small. In some cases, they will be very large and intrusive and so on. So in this case, we saw actually example where there was 8 a.m. in the morning, around 605 data, and actually megawatt power went up because of the higher demand. And this disturbance caused turbine speed to immediately went down, and even it went down below that regulation for the unit trip. And because of that, you can see just the feedback action of the steam valve where it tries to respond and tries to maintain the RPM at a certain level, which is 3,600. So just taking this data from the past, because that power plant had more than several examples in their data historian of this kind of the behavior, we were able to identify simultaneously using complete closed loop system identification data two process models. One is a pure process model behavior, which explains the behavior between the steam valve and the turbine speed. And another model, it is the model which explains the behavior between the disturbance, which is the megawatt load, and the turbine speed. And with that, actually, we were able to accurately and precisely calculate a feed-forward control action and avoid unnecessary trips and spikes and reduction of the loads, what you can see on this picture. So this is, again, a nice example where you can help the plant, again, without doing intrusive. So you can imagine what would be the step tests here. So somebody would need to put steam valve position in manual mode and then bump it, and then be very careful because you need to maintain this turbine speed at a fixed position, and you cannot have a violation because you will trip the unit. So imagine how dangerous it is to have this kind of the step testing here. And then the last example, actually, it is coming from cryogenic distillation plant. And it is a multivariable closed loop MPC, model predictive control identification, where the first, actually there are four trends. I will go from the top. First top trend, it is actually control variable or a CV of an MPC controller. This was actually dynamics matrix controller from AspenTech implemented in that plant. And it had some problems because the models were not so precise and accurate. And because of that, it produces some undesirable control actions. We have realized that the problem is inside of the models because they were not so accurate. And actually, we have again taken the data from the data historian when this DMC controller was on and running. We haven't done any kind of the step test. We haven't turned off the MPC controller. We haven't played with the manipulated variables to bump them in some desired manner for several times. So as you can see, the top trend presents the argon purity, which actually it is controlled by manipulating three manipulated variables. One is airflow, and on the second trend, another one is gas oxygen flow, and the third MV, it is liquid nitrogen reflux flow. And actually the main problem what they had, every morning at 7 a.m. when the cost of the power went up, they needed and they wanted to reduce the plant capacity in order to save on the power. Every evening when the costs of the power went up, they wanted to increase the plant capacity in order to take leverage of the smaller costs of the power. So every time when they have done this kind of the transition, due to the model imperfections and due to the process non-linearity, because you are changing the plant capacity and by that going to different non-linear regions of the plant, they have a serious oscillations and the problems of the MPC controller, what you can see on the top trend on the right side. Taking this data, again from the Excel and data historian, we were able to identify simultaneously three transfer functions completely in closed loop mode, where you can see that manipulated variables were moving not in the step manner, but in the manner how you would see normally in the plant, like a complex trajectories of the MVs. And plunging improved three models, what we have identified back to the DMC, we have tremendously improved the behavior of the DMC controller during that transition phase. So this is a nice and very powerful example that even, I would say, the highest level of the controls like model predictive controllers can be improved with a significant reduction of the step tests and just taking the data from the past. Okay?
Okay.
So with that, actually, I would like to close the chapter about the system identification and what we are capable to do. And now, once you know the models, once you have been identifying true and accurate process models, now with this kind of the models, you can do amazing and powerful stuff. You can tune PID controllers, you can implement and design very nice, attractive, and very powerful advanced process controllers inside of the DCS or a PLC, or even you can build the model predictive controllers and put them as the ultimate master of your plans. So the PyTops actually technology, what I was explaining when I was explaining the system identification part, consists of two parts. One is used for system identification, and then another part, it is used for PID tuning and APC design and optimization. So please give me several minutes just to go through this part also. So again, in the PID tuning arena, it is very famous, and I would say familiar with all chemical engineers and maybe other engineers, mechanical, electrical engineers, and so on. There are a lot of tuning methods what you can use, and most of the times people like to tune based on trial and error. What we have invented, and yes, there is also idea that it is possible to invent something. We have invented new PID tuning standard, and we like to call this like a multi-objective PID tuning. So based on the identified process control models, we are able to accurately and mathematically tune PID controllers in the several case scenarios. So before I explain that, let me try to share one thought with you, if you don't mind. So
Please.
I would say 90 to 95%, or maybe, I don't know, even more, tuning packages can tune controllers only on one thing, and this is if you do a set point change. So if you plunge or start up many tuning packages, even auto tuning packages, they will be able to tune the controllers, but what they will request you to do or what they will do inside of the package, they will tune and calculate PID tuning parameters based on the set point change. So one question which I always like to ask is, okay, so we are tuning based on the set point change. Then let's say in each plant which tackles with the liquids or even maybe gases which are finally liquefied or so on, in some cases even solids, there are a lot of, let's say, level controllers. Level controllers in the distillation tanks, level controllers in the distillation columns, level controllers of the storages, level controllers of the reactors, or maybe of some buffer, reflux drums, and so on. So actually, this is the question for you. What do you think, how many often do these level controllers change their set points, or operators, how often they change the set points of the level controllers?
Well, I know there's a lot of them where it's a kind of a set and forget situation because, they're trying to maintain, in many cases, they're trying to maintain a level or a temperature. And so in a lot of them, especially the standalone ones, it's a set and forget. When it comes to, more advanced process control and where PLCs are involved, the set points do change based, something like, for instance, sometimes based on a product. So if you're running different products through the same system, the set points definitely have to change. Um,
Okay.
what are your thoughts?
Yeah, actually, I agree with you. So there are certain cases where nobody is changing the set points of the controllers, and they are always at some fixed desired position.
Hmm.
And there are controllers which have regular, or I would say, uh, some rare uh, time periods when they change set point of their controllers, right?
Hmm.
So depends of the nature and needs and objectives of the controller, you would conclude that sometimes set point is a fixed value, sometimes it is like a changeable value,
Hmm.
right?
Hmm.
So the main question is why to tune all controllers on the set point change if I would say maybe 40% of the cases nobody is changing the set point of the controllers.
Hmm.
So honestly, I do not see the sense and the logic inside of that. But okay, so that's why what we have created the PID tuning methods, which actually will help you to understand the needs and objectives of each controller, and based on the real needs and objectives of each controller to tune the controllers. So let's say in the case example of the level controller, you don't want to tune the level controller on the set point change because you want to always have a fixed level at 50%, but you want to fight against disturbances, which is maybe flow in or flow out, right?
Yeah.
So in that case, you don't want to tune controller on the set point change, which will never be changed, but you want to tune controllers on the disturbance change or disturbance impact. And tuning controllers many times on the set point change, especially when you are doing that by trial and error, or with some very sluggish tuning rules like IMC rule or lambda tuning rule, you are not able successfully to fight against disturbances. So actually, and in other cases, maybe like a flow controller which has got the pressure variations of it. Let's say you have a steam flow controller, it is a gas, and the gas pressure fluctuates. In that case, you want to change the set point of the flow controller because you want to manipulate with this flow controller to keep energy balance stable. But also you want to fight against the internal disturbances, which are the pressure variations. So actually what we have done, we have given the user the option to decide how he wants to tune a flow, how he wants to tune a PID controller. So actually he can tune a PID controller based on the step change, based on the ramp change, or even based on the complex trajectory of the set point, what you can see many times in the slave or secondary cascade controllers.
Mm.
Then also we have given option to user that he can introduce disturbances like pulse, step, ramp, and sign disturbances, and tune controllers based on specific disturbance what it is created inside of the tuning procedure. Also, you can tune controllers based on the noise. You can set the PID output rate of change. So you can actually have a constraint tuning. Let's say one case example is you have two reactors or maybe two distillation columns in series. And the bottom of the first distillation column through the pipe, it is connected to the second column. And this pipe is actually a feed to the second column. And in between on that pipe, you have a valve. So in that case, you don't want to open that valve for huge amount in a certain small time period, because this abrupt change in the valve position can cause a big flow difference, and it will actually be presented as a downstream disturbance to the downstream unit, right?
Mhm.
So what you can do, you can set up the tuning based on desired rate of change of your valve position. Let's say in the one case example is, let's say maybe you don't want to open this valve more than 2% in second, because you have recalculated that this is maybe 2 tons per hour or something, and this is a huge amount of flow which can go to the downstream unit and cause a huge disturbance. So now you can set up the constraint when you are tuning the controller, and you can say, okay, please tune this controller as best as possible, but please maintain this constraint that I don't want for this valve to change abruptly, sudden for a big move. So this is another case scenario what you can do. Also, as I said, we can identify valve stiction, the real valve stiction from the valve, and we can use that value or a percentage, how good or how bad this valve is, and we can implement this value inside of the tuning procedure. So actually what you are getting very precise and tuned PID controller, where the constraint or the problem of the real identified valve stiction is there. And with that, you'll get slightly different tuning parameters, which will help you to tackle again the valve stiction. So this is another power and feature what you can get. And also you can create like adaptive controllers or again scheduling controllers, where you can tune different controllers for different nonlinear regions of the plant or a unit. And with that, actually, the goal of what I'm trying to say is that once you know the basic objectives of each PID controller, you can approach and tune this PID controller to match these needs and objectives. It's not that you'll tune everything on the set point change and go home and you're done. So this is the power, actually, what you are getting here. So this is one case scenario where actually I want to explain the benefits and actually how we are doing that inside of the PyTops. And let me just use a pen in order to maybe highlight some things. So actually here I'm highlighting the part of the software where actually the users can see identified process model. This is a transfer function model in the time domain, and actually what is identified, there is a dead time identified, which is in minutes, so it is almost 80 minutes. So we are able to identify even processes with very slow dynamics and very slow big dead times and time constants. There is a process gain which is around 56.6 and engineering units, and then there is a time constant of almost 36 minutes. So I would say this is a very slow controller, okay? So we have plunged the model from one window where we have done system identification into the window where we are tuning the controllers. And also what we have done, we have made a simulated set point change from 1500 to 1700, and you can see that as a step change of the blue line on the first left trend, right? Okay, so the second thing, so now we are tuning on the set point change, and also this controller is requested to be tuned on the disturbances. So now what we have done, we have injected a pulse disturbance, which is not a typical step pulse disturbance, but it is a pulse disturbance with a lag or with a delay, as you can see it here. So this step up or this pulse disturbance going up actually corresponds to this drop of the CV from the set point. You can see this bump going down. Also, we are introducing in the opposite direction the pulse or a step disturbance with a lagged behavior. And this second introduced step disturbance, actually it is corresponding to this hill of the control variable, which is deviating from the set point. You can see here. And the third thing, simultaneously, what we are doing on the top of these two pulses or steps, we are introducing a ramp disturbance, what you can see here. And actually, this ramp disturbance is causing your control variable to continuously deviate from the set point, what you can see here. So now with this kind of the simulation, also we are introducing the noise on the top of the control variable, which is translated to the controller output, as you can see. Now also controller output is noisy. And now with this kind of the simulation, we are able to tune this controller with very slow dynamics based on several things. First, based on the set point change, which is a step change. Based on the injected pulse and ramp disturbances, and also based on the real noise which you can see inside of the data. And ultimately, on the right side, you will see the tuned PID tuning parameters, which you can automatically plunge directly in the PLC or a DCS once you're done with the tuning. So this is the power of it. Also, what you can do, once you know all the models, process models, it is possible to use PyTops and to accurately calculate APC parameters such as feed-forward lead and lag parameters and other parameters. We have seen many times, especially in the power plants and maybe some other plants, people are just putting arbitrary numbers. They feel that 0.5 is a small number. They will plunge it as a lead. They will say, okay, maybe 0.8 is slightly bigger number. They will plunge it as a lag, and they will feel that these numbers are good. But 0.5, considering range and sensitivity, can be weak parameter or maybe can be a too aggressive parameter. Nobody knows. But knowing process models, knowing disturbance models, what you can accurately identify in PyTops, you're actually able to mathematically calculate feed-forward parameters like lead, lag, feed-forward gain, and so on. So with that, we are actually stopping the era of trial and error guessing. Also, you can build nice inferential controls and calculate inferential model, which you will use for inferential control. You can design and mathematically calculate Smith predictor or dead time compensator. You can build nice constraint override controllers, which will save you against some constraints like equipment constraints, unit constraints, process or economical constraints. You can also build nice adaptive control. It can be three ways, like auto-adapting dead time, gain and time constant, or just doing a gain scheduling, or even a valve characterizer. And also you can build powerful production rate maximization or waste minimization schemes and precisely calculating the parameters which will run this kind of the advanced process control logic and techniques. And also you can smooth out the grade operations and transitions. So with that, you can build a lot of things, and we like to call PyTops like what is screwdriver for the electricians. Actually, we like to call that this is a screwdriver or a tool for process control engineers. So with that, let me just give you a brief table where actually we have done extensive study of our PyTops technology and compare that technology with competitors' technology. So let's say in approximately 10 rows, I would like to summarize. So PyTops can be run in offline Excel version, and also you can connect it as an OPC client and run it in online version, where many other technologies can be just placed as an OPC or online version, where actually you need to do step tests. Then system identification in PyTops can be done based on completely oscillatory closed loop data. You can do system identification using non-steady state closed loop data, or you can use system identification based on cascade closed loop data, as you have seen. You can do multivariable system identification using either open or closed loop data. It is up to you. And you can use data to do a system identification while the MPC controllers were on and running. You can identify the valve stiction and the mechanical issues inside of the valve, and you can optimize your controllers based on the amount of the valve stiction. You can isolate and you can identify the pattern of unmeasured disturbances while identifying true process models. You can identify process or equipment nonlinearities using PyTops. You can tune slave controllers or cascade controllers based on the complex setpoint trajectory, where definitely there is no tuning procedure for that in other technologies. And many other things like calculate gap control, calculate mathematically feed-forward parameters, inferential, dead time compensation. You can tune controllers based on different disturbances or constraint tuning like rate of change and many other things as well. So with that, actually, I would like to slowly close out this discussion and actually presentation and invite the listeners to visit us at www.PiControlSolutions.com or just send us an email at info@PiControlSolutions.com.
Well, I appreciate you going through all of that, Ivan. I think, one of the things we learned by watching this presentation was that, you know, what you have designed as a solution not only can be done without bumping the actual process, without being online and disturbing the system, which has all the can have all the results that you don't want, and we talked about in great depth. But by using that historical data, and the by being able to take the knowledge of the people who actually been running this system for years, you can do a lot of things that other companies struggle to or just plain can't do with their turnkey solutions. So I think you can see also from this presentation where and I'm going to guess most of your customers partner with you. They're not just buying a software product, but they're actually buying some of your services to, if you have a very important loop that you got to get fixed, it's just you get too much oscillation, too much variability. It's something where you've maybe tried other solutions and you just can't get it right. This might be a time where you turn to, at least reach out to the people at PiControl Solutions and see if they have a solution to the issue you're running into. You saw the list of applications they worked on, and their solution does include a lot of things that you'll notice other companies don't address, right? And I think it's because they have a unique methodology of going after, especially by using the historical data. You can see, I mean, you can actually take advantage of multiple, days, weeks, months of actual disturbances and changes in set points that would just be, unrealistic to shut a plant down for a month to try everything that you could try. So I'm going to guess that most of your customers are engaging you not, for not just a software solution, but also for some services and possibly some training as well. Would I be right in that?
Yes, definitely. There are customers who would like to be well prepared and trained and use our technology so they can try to tackle with their problems internally, because most of the time this is their position or their job duty.
Hmm.
And many cases there are customers which are trying to learn from us, giving us some kind of the preliminary or a smaller project like a tuning project or APC project. And then what we'd like to do, we don't like to keep people out of the project. Actually, what we like to do, and this is our motto, what has been running for years and years, we like to include one or two the most experienced operators, one or two the most experienced chemical engineers,
Hmm.
and one or two the most experienced or actually willing to learn process control engineers. We create a team of people, and then we jointly create a step procedure how to tackle with some kind of the problem. And while we are doing that, we are showing that how we are doing that so they can learn and use the technology itself.
Yeah, excellent. Well, Ivan, again, I just want to, before we close out, was there anything else that you wanted to talk about or mention?
Actually, no, I think this is enough for the first presentation. I hope that there will be plenty of other presentations as well. So for that, yeah, I'm done and I'm happy how it went.
Well, I want to thank you for coming on the Automation Podcast and taking all this time out of your busy schedule to really kind of bring us up to speed on your solution and how you take a unique, uh, uh, how you take a unique way to solve some of these complex applications. And really just appreciate you coming on the show.
Okay, thank you very much. And yeah, I'm inviting the other users and listeners at least to visit us, maybe ask a question if they have, or at least to try a trial version of the technology and to see what it is capable to do.
Well, I hope you enjoyed that episode. I know I did, and I think it's really cool that they don't have to bump the process to actually tune the loops. Very, very cool. And with that said, if you enjoyed this episode of the show, please consider giving us a like and a sub. And if you're listening to the audio-only edition, please consider giving us a 5-star review, which helps us really broaden our audience and find new vendors to come on the show. And thank you to all of you who already have done so. I really appreciate it. Now, that said, you'll always find all of my affordable online training courses over at theautomationschool.com, and you can support the show or just follow me over at automation.locals.com. With that said, I want to thank you for watching and wish you all a very happy, safe, and healthy week. And until next time, my friends, peace.